Good morning. In the last lecture, we had seen about different types of error that may occur in a measurement system. We had looked into systematic errors, random errors, and induced errors. And we have also seen how systematic errors and induced error can be handled. Okay, so in this lecture, we would start on working with random errors. So they've seen that the effect of systematic errors can be estimated and corrected. The bias that is introduced by systematic errors can be corrected. However, random errors are random, as the name implies, and therefore for any single measurement of random error for say from a single measurement we can't find any correction factors, but we will be able to find an estimate of the extent of error. Okay, and that is only an error statistics can be used to get an idea of what should be the actual value. So if you have a measurement here, the extent of this error band within which the actual value will lie, that can be estimated, that can be found out if we are sure about the statistics of the instrument, or statistics of the error in the instrument. Okay, now what do you mean by statistics in this? Okay, so we have already seen that the random errors can be reduced only by taking multiple measurements of the same quantity. Okay, now let us say you have multiple measurement. What should be the final quantity? Okay, now there are various choices for which are candidates for the final value. One is the average of all the measurements, which is usually called as the sample mean. Okay, which is just the average of all the measurements if you have n measurements, and as the number of measurements tends to infinity, the sample mean tends to go to mu, which is called as the true mean of the measurement. Okay, so after mean we have median, which is the middle value when the measurements are measurements in the data set are arranged in either ascending or descending order. Let us say if the measurements are like say 1.5, 1.6, 1.8, 2, 2.5 or something like that. Okay, so the median would be this value 1.8 and the mean of this data set would be approximately 1.9. Okay, and mode, which again is the most frequently noted measurement. So these are the three candidates for the measurement, for the final value, for the average or something that we want to take. And out of these, the sample mean is the most likely candidate to be the true value. Although median is more easily computable. I have to just sort the data set in an ascending or a descending order and choose the middle entry. However, there is also this issue of precision of measurement, precision and accuracy of measurement. Okay, by taking the mean, you are improving the accuracy of the measurement. Okay, so if there are n number of measurements, by taking the average, you're sort of taking out the random variations and getting something that is more accurate than any of these measurements. Okay, now however, let us say you have three cases, or you have two cases. One is in which there are three measurements which are spread like this, and another in which there are three measurements that are spread like this. Okay, so obviously in both of these cases you get the same mean value. However, obviously one of them is more precise than the other one. So the precision of this is actually correlating with the spread of the measurements, and it is not good enough to say whether this only taking the maximum and minimum value is also not good enough to quantize this spread of measurements. Okay, because it is possible to have such a scenario. Let me put that in. Okay, it is possible that you have a scenario where you have a set of measurements that look like this, and another set of measurements which look like this. So it is quite clear that in the second case most of the measurements are bunched together and there are a few outliers, while in the first case, in most probability the error is higher. So this is actually a better case than this one. Okay, and that is intuitively we are able to say that because the high error cases are infrequent in this case. However, if you only take the maxima and minima, this has a larger spread and this has a smaller spread. Okay, so just having the average value is not giving you any idea of the precision of the instrument, and just measuring the spread, that is the maxima and minima, is not giving you enough information. Even that is not giving you enough information about the precision of the instrument, because there can be cases where a large error can occur with a very low probability. Okay, therefore we need to up our ante and go for better mathematical tools. Okay, and for this purpose we will be using the variation of variance and the standard deviation. Now variance, as you would have studied, is the mean of square of deviations from it. So if you have a true mean, the deviations from this value, say x1, x2, so x1 minus mu the whole square, or x minus mu the xi minus mu the whole square, the summation, and divided over the number of measurements, is going to give me the variance, and the square root of the variance is called as the standard deviation. Now there is one problem here, because this we are supposed to use mu, and however in practice you don't have the true mean, you only have the sample mean. Okay, so because of that there is always a danger of an underestimation of the variance. Okay, and because of that we have to modify this. We have to actually get a correction factor, the Bessel correction factor, which is n by n minus 1. If you apply it, the variance formula changes with the denominator being n minus 1 instead of n, and so does the formula for sigma. Note that in this case you should have at least two measurements are needed now to make any sense of this, whereas in the previous case, when you have only one measurement, there was a theoretically you can compute the variance and standard deviation for that. In this case, in a practical case, you at least need to make two measurements, but again this is a severely low estimate of it. Let's go into the number of measurements that may be required on the, and other concepts as we proceed further into the lecture. Now, when you have an n number of measurements, a lot of measurements, and you want to represent them, the histogram is a simple way to represent the distribution of the measurement data. In this case, the measurement range is split into n number of different bins, and the number of measurements in each bin is noted and recorded in a bar graph that looks like this. Okay. Now, the point is, what is this n? Because if there are too many bins, then there will be too few measurements coming in each bin, and if there are too few bins, then there are too few points overall. So too few bins would mean that then there are too few points to discern what the distribution is. Now in this case, if there are 5 bins, you are able to say that the distribution has a shape something like this. Instead of that, if you only had 3 bins, okay, then you have much less information about the shape of the distribution. So an optimal value, optimal number of bins has to be figured out. Okay, and to help this, we have a few thumb rules that can be followed. Okay, and one is the Sturge's rule and another is the Rice rule. So as per the Sturge's rule, the number of bins is given by this formula, which roughly translates to the logarithm of 2n base 2. And in Rice's rule, the number of bins is 2n raised to 1 by 3. Okay, if you compare the number of bins that are predicted based on the number of measurements, then by Sturge's rule, you get these values, and which can be rounded off to this number of bins, and by the Rice rule you get this number of bins. Typically the Rice rule tends to give more number of bins as n increases. Okay, so better use and estimate the number of bins to be between these two values, and if the distribution is suspected to be symmetric about some mean value, then it will be clever to use an odd number of bins, so there is a central bin which captures the maximum of the peak of the distribution. Okay, note that these rules are only guidelines. They need not be strictly abided by. If you feel that based on your data the number of bins have to be changed to be chosen different from what is predicted by these rules. Okay, proceeding further, now as the number of the sample size increases, okay, then the sample mean is going to go towards the true mean that we have seen while defining the mean itself. Okay, and this will also mean that the number of bins that are present is also increasing. So the discrete histogram will tend to become a frequency distribution curve. Okay, so if instead of the number of bins, we tabulate the the proportion of data within a bin. Okay, or rather than, so if you take a bin, instead of tabulating the number of points in that bin, if we tabulate the proportion of the total number of data, total amount of data falling in that bin, and increase the number of bins towards infinity, you would end up with a probability distribution curve. Okay, now if we center this probability distribution curve around so on any way, so from the probability distribution curve you can say that the probability that the measured value is between d1 and d2, and if you say this is h of d, that would be given as the integral from d1 to d2 h of d. Okay, and the probability of say a value, probability of d being less than d0 will be integral minus infinity to d0 h of d will be given by this expression. Okay. Now this is the general case. However, in most measurement systems which are corrupted by random errors, the usual shape of the probability distribution is something called as a Gaussian distribution, and whose shape is like a inverted, is like a bell. So that's why it is called as a bell curve. And the expression for h of x is given by this one, where sigma is, as we have seen earlier, is the standard deviation, mu is the true mean, and x is the value that we are looking at. Okay. Now instead of x and mu being used, we can use a deviation d, which is x minus mu, okay, and get the expression in terms of d. In fact, it can be improved further by normalizing it and using z is d minus sigma or d by sigma, and get the expression in terms of sigma itself. Okay, so from that, what we have done here is that we have got the curve for a distribution, for a Gaussian distribution, whose mean is 0 and whose standard deviation is 1. Okay, it is mapped to that, and any analysis on that now can be scaled and shifted to any arbitrary Gaussian distribution with a mean mu and a standard deviation sigma by backtracking appropriately. And this sort of Gaussian distribution with zero mean and unity standard deviation is called as the standard Gaussian curve. Okay, and from this you can tabulate this integral, which actually basically means that f of z1 is basically the same as probability of z being less than z1. Okay, so that one is can be tabulated in a table. Okay, and from that we can gather some sort of some few rules, or few, not rules, few properties that we can see. That is, the probability of z being between z1 and z2 will be the same as f of z2 minus f of z1, and since this is centered at 0, centered at z equal to 0, you will have f of minus z is 1 minus f of z. Okay. Okay, let's see how that happens. Okay, because now f of minus z is, so if I have z here, this is minus z, this is centered at 0, f of minus z is this part of the curve. Okay, and f of z is this part of the curve. I am not putting in this manner. Okay, so let me again do that so that it is a little bit easier. It is this part of the curve going from this to z. Okay, and 1 minus f of z is the rest of the curve, that is here. Okay, however, due to symmetry, this portion should be the same as this portion. Okay, which would mean that f of minus z should be equal to 1 minus f of z. Okay. Now this table, the table of the standard Gaussian distribution or the z distribution, that can be used to analyze a given data distribution, the distribution of a set of measurements, okay, and see whether it fits a Gaussian distribution, or if it is assumed to fit a Gaussian distribution, what is the probability of any particular area, any particular measurement being within some bounds. Okay, so this is the typical table of a Gaussian distribution. Okay, so we can say that the probability of something is between minus z and z, minus z1 and z1 is given by this expression. Okay, and the probability of something greater than z1 is the same as the probability of something less than minus z1. Okay, which is given by 1 minus f of z1. So these simple rules can be recalled. Okay, and due to the shape of the Gaussian distribution, the expected number of points outside plus or minus d, okay, that is going to fall really rapidly as d increases. This can be seen quite easily. So as you say, as z changes, you see that the number of points outside z, say for example, let us say you want to see, so this is the number of points between z1 minus z1 and z1. Okay, so the points outside this would be 1 minus 2, or rather it will simply be twice of 1 minus f of z1. However, you see that and so you have f of z here. Now as z changes, f of z is rapidly changing. Okay, now if you see f of 1, it is 8.4. okay, f of 2 is 9.7, f of 3 is 9.99, 0.97, 0.99. Okay, so there is a rapid change in the value of f of z as z increases. So there is this graph tapers quite sharply. Okay, and that can also be seen, by seeing the deviation boundaries at plus and minus sigma. Okay, so from the standard Gaussian table, we can say that 68% of the data is between plus and minus sigma. Okay, 95% of the data approximately is within plus or minus 2 sigma, and almost 99.7% is between plus or minus 3 sigma. And if the table was extended further, we would see that within plus or minus 4 sigma, it is almost 99.99% more than, and which leaves a far lesser number of points outside that boundary. Okay, now see, we always have a finite amount of measurements. So whenever you are trying to make a distribution, okay, you have a finite number of measurements, and for this measurements you calculate a sigma. Okay, or rather you leave out a sigma for now. You calculate a mean. Okay, and this mean may be different from the true mean that would have been obtained if you had done infinite number of measurements. In fact, if you have taken n points, made a set of measurements and taken a mean for it, and done this a lot of times. So with n, with the first experiment, you get some x1 mean, and then you have x2 mean, then you have x3 mean. Okay, now all these would be, again, if you take these as the data points and make a distribution of that, these data points again would form a Gaussian distribution around the true mean mu. Okay, the sample means of all these data points, all these various data sets, would form a Gaussian distribution or centered around the true mean. Okay, and since it's a Gaussian distribution, there will be another standard deviation for these means. Okay, and this standard deviation, which is called a standard error of mean, okay, which is the standard deviation of the Gaussian distribution of the sample means, that is related to the standard deviation of the true Gaussian distribution by this relationship. Alpha is sigma by square root of n. Note that as n increases, alpha decreases. So as the number of measurements increase, the surety that the sample mean is equal to the true mean increases. Of course, the standard error of mean can now be used to predict the error between the mean of a finite set and the true mean. Okay. So what we are basically saying is that we are saying that the probability that this error is between alpha and minus alpha is 0.683 or 68.3%. Okay, just like we had seen the probability distribution graph having 68.3% between minus sigma and plus sigma range. Now, how will this be useful? We can use alpha to get an estimate or to get an idea of how reliable is the, or how less or more is the error of mu minus x mean. Okay. And the standard deviation of the Gaussian of the sample that we have taken, that will give an estimate of any arbitrary, the error between any arbitrary value measurement xi and x mean. So this both can be combined together to get an estimate or an estimate of what is the error between xi and mu. This has to be, this really doesn't matter. Okay, so what is the error between xi minus xi and mu? That can be used, that can be got by combining sigma and alpha. Okay, in this manner. Okay, so if you have an application where repeated measurements are not possible, then probably you will be able to have only one measurement. Okay, and if you have an idea of what is the standard deviation of the true distribution, and also an idea of what is alpha. Okay, and if you want to know, so for example, if you have measured if you have a single measurement and that is coming out to be x, okay, and what is the probability that, or what is the error bound between x minus mu, now without knowing what is mu. Okay, and usually you want to get it as with a 95% confidence limit. Okay, so if this is what you want, and let us say that how do you get this 95% confidence limit? So what we want to get is that we want to get these boundaries so that 95% of the graph is within these boundaries, and what we are saying is that this is centered around mu. This graph is centered around mu. Okay, and your x is somewhere within this range. Okay, it can be one of these, any of these points. Okay, so what we want to do is then this translates to us trying to figure out at what point is this half 95% by 2, that is 47.5%. Okay, now on top of this what we had was, okay, I deleted all the graphs. Okay, what we had was the z distribution in which we have f of z, that gives us what is the graph beyond up to this value. So there is a 0.5 here, okay, and there is some more here, and this 0.5 plus x is being given in this table. Okay, we know, for us, we know that x is 0.475. So what we want to look at is at what value of z does this come out to be 97.5. Okay, and if you look at it, it comes at 1.96. Z is 1.96. Okay, or the deviation d is equal to 1.96 times sigma. Okay, now we have said that we want 95% confidence. So what this means is that x minus x mean, the probability of this, or the probability of mod of x minus x mean less than 1.96 sigma. Okay, this is less than, or this is equal to 0.975. Okay, and similarly the probability of mu minus x mean less than 1.96 alpha, this is also 0.975. So from these two equations, we can say that the probability of mu minus x being between these values, okay, would be 95%. Okay, so, and that error is 1.96 sigma plus 1.96 alpha. Okay, now here for to making the estimate, okay, particularly in cases when you have a single measurement and you want to make a prediction of what is a possible error, we can use the z distribution table. Okay, however, here we are assuming that what is sigma and what is alpha. Okay, we are assuming that we already have an idea of this from past experience with the instruments. Now, there is still one question that is not really clear. So all the above analysis was done under the assumption that the data actually follows a Gaussian distribution and we have some idea about the mean and standard deviation of the data. Okay. However, how are we actually sure that the data conforms to the Gaussian distribution to any particular amount of accuracy? Okay. We look at that and also some aspects of how to use this data, okay, and how to predict how best fit is happening in the next class and in the next lecture. So these are the chapters that you can look at. One is on the a chapter from Nakra and Chaudhary on statistics and normal distribution. Okay. And other is chapter 4 on from Alan Murray and Eliza Lengari. That's again on statistical measurements and random errors. Okay, so with that we come to the end of the lecture. Thank you for your patience.